You know, people ask me all the time, why does mathematics work so well in describing the universe? They say, look, we sit in our offices, we invent these abstract symbols, we play with equations on blackboards, and then we go out into nature and holy smoke, the universe actually obeys these rules we just made up. How is that possible? Isn't that the most remarkable coincidence you ever heard of? And I gotta tell you, this question bothers me too, but maybe not for the reasons you think. Let me start with something that might surprise you. Mathematics is not really invented in the way most people think it's invented. When a mathematician sits down and creates a new mathematical structure, they're not pulling it out of thin air like a novelist invents a character. They're discovering relationships between ideas, exploring what must be true if you accept certain starting assumptions. It's more like exploring a landscape that already exists than building a house from scratch. But here's where it gets interesting, and this is what I want to dig into today. Even if we say mathematics is discovered rather than invented, we still have to ask, discovered from where? Is mathematics something that exists out there in the universe, waiting for us to find it, or is it something our brains construct because that's how our brains work? And more importantly, why should the particular mathematics we find useful happen to match the way nature actually behaves? Now, let me tell you about a conversation I had once with a philosopher friend of mine. He said, Feynman, isn't it amazing that the universe is mathematical? And I said, wait a minute, what do you mean the universe is mathematical? The universe is just doing whatever it's doing. We describe it with mathematics. There's a difference. If I throw a ball, the ball doesn't know it's following a parabola. The ball doesn't solve differential equations in mid-flight. It just goes where the forces push it. We're the ones who come along afterward and say, hey, that path looks like it follows this equation. The mathematics is our description, our map of the territory. It's not the territory itself. But then he pushed back, and this is the clever part. He said, okay, fine. Mathematics is just our description. But why is it such a good description? Why can we predict eclipses thousands of years in advance using equations? Why can we calculate the magnetic moment of the electron to 10 decimal places and have it match experiments? If mathematics is just something we invented to organize our thoughts, why does nature cooperate so perfectly with it? That's the real mystery. And you know what? He's right. That is the mystery. Let me give you an example that really drove this home for me. When I was working on quantum electrodynamics, we were trying to calculate how electrons and photons interact. We had this mathematical framework, and we kept running into these infinities, these absurd results that made no physical sense. For years, people thought maybe the whole mathematical structure was wrong. But then we figured out this technique called renormalization. We found a way to reorganize the mathematics, to absorb these infinities into redefinitions of mass and charge, and suddenly everything worked. We could calculate things, make predictions, and they matched experiments to incredible precision. Now here's what struck me. The mathematics we used, this renormalization procedure, it wasn't something we derived from first principles. It was almost like a trick, a mathematical game we played to make the calculations work out. And yet, nature didn't care that we were playing games. Nature matched our predictions anyway. It was as if the universe was saying, yeah, okay, you found a mathematical pattern that happens to match what I'm doing. Good for you, here's your reward. But why should that work? Why should our mathematical tricks correspond to reality? Let me come at this from another angle. Think about the history of physics. Newton comes along and he invents calculus, well, he and Leibniz, but let's not get into that fight. He invents calculus specifically to solve problems about motion and gravity. He needs a way to describe how things change continuously, how velocities change into accelerations, how orbits curve through space. So he develops this mathematical machinery of derivatives and integrals, and it works beautifully for mechanics. But then a century or two later, people start studying electricity and magnetism. Completely different phenomena, right? You've got charges and currents and fields, nothing to do with planets and apples falling from trees. And yet, when Maxwell sits down to work out the mathematics of electromagnetism, what does he use? Calculus. The same mathematical framework Newton invented for mechanics turns out to describe electricity and magnetism perfectly. Then we get to quantum mechanics, and guess what? We need calculus there too. In fact, we need even fancier mathematics, complex numbers, linear algebra, group theory, all this abstract stuff that mathematicians had been playing with for their own amusement. And suddenly, it's exactly what we need to describe electrons and atoms. So here's the pattern. Mathematicians invent or discover, or whatever you want to call it, they develop these abstract structures for their own reasons, often just because the mathematics itself is beautiful or interesting. They're not thinking about physics at all. And then physicists come along decades or centuries later and find that these mathematical structures are precisely what they need to describe nature. It's like nature is reading the mathematics textbooks and saying, oh, that's a nice group structure. I think I'll use that for particle symmetries. How does that happen? One answer, and this is what a lot of people want to believe, is that mathematics is the language of the universe, that there's some deep Platonic realm where mathematical truths exist eternally, and both mathematicians and the universe itself are tapping into this realm. The universe obeys mathematics because mathematics is the underlying reality, more fundamental than matter or energy or space or time. Everything else is just mathematics in disguise. But I gotta tell you, this makes me uncomfortable. It sounds too mystical, too much like we're saying mathematics is some kind of God, and it doesn't really answer the question, it just pushes it back a level. If the universe is fundamentally mathematical, why that mathematics? Why differential equations and Hilbert spaces? Why not some other kind of structure entirely? You haven't explained anything, you've just given the mystery a fancy name. Here's another way to think about it. Maybe we're looking at this backwards. Maybe it's not that the universe obeys our mathematics. Maybe it's that we only call something mathematics if it's useful for describing patterns we see in the universe. Think about it. Human beings evolved to survive in this universe. Our brains evolved to recognize patterns, to predict what's going to happen next, because that's how you avoid getting eaten by a tiger. You see the grass moving in a certain way, your brain calculates, tiger approaching at this speed from that direction, better run. That's mathematics, primitive mathematics maybe, but it's mathematical reasoning. So, our brains are pattern recognition machines built by evolution to work in this universe. Is it any surprise that when we formalize our pattern recognition into something we call mathematics, it works well for describing the universe? We're part of the universe. Our brains are made of the same atoms that make up stars and planets. The patterns our brains recognize are patterns that exist in nature because we evolved to recognize exactly those patterns. But wait, that doesn't quite solve the problem either, because modern mathematics goes way beyond anything evolution prepared us for. Evolution didn't need us to understand quantum mechanics or general relativity. There were no tigers in the Pleistocene that required you to calculate the curvature of space-time to avoid them. And yet the same mathematical intuitions we evolved for everyday survival, when we extend them and formalize them and make them rigorous, they still work for describing black holes and quarks and the early universe. That seems like more than just coincidence. Let me tell you about something called the unreasonable effectiveness of mathematics. This phrase comes from a physicist named Eugene Wigner, and he wrote a whole paper about this question. He pointed out that mathematics is unreasonably effective in the natural sciences. The mathematics we develop often works far better than it has any right to. We come up with an equation to describe one phenomenon, and then we find the same equation popping up in completely different contexts. For example, the wave equation. It was first derived to describe vibrating strings, like on a violin. Then people found it describes sound waves in air. Then water waves on the surface of a pond. Then electromagnetic waves, radio waves, light. Then quantum mechanical probability waves. The same mathematical structure over and over again in completely different physical situations. Why? What do violin strings have to do with light? What do light waves have to do with electrons? At the mathematical level, everything. At the physical level, they seem totally unrelated. Or here's another example, the mathematics of complex numbers. When mathematicians first started playing with the square root of -1, people thought it was nonsense. They called them imaginary numbers because they didn't correspond to anything real. You can't have -1 apples, so how can you take the square root of it? It seemed like pure mathematical game playing with no connection to reality. But then, when we developed quantum mechanics, guess what we needed? Complex numbers, not just as a convenience, but as an essential part of the theory. The wave function, the fundamental object in quantum mechanics, is complex valued. You can't do quantum mechanics without complex numbers. So this piece of mathematics that seemed utterly divorced from physical reality turned out to be absolutely necessary to describe the most fundamental level of nature. How did mathematicians playing abstract games in the 17th century stumble onto something that would turn out to be essential for physics in the 20th century? I think part of the answer is that we notice the cases where mathematics works and we forget about the cases where it doesn't. This is a kind of selection bias. There are probably lots of mathematical structures that don't correspond to anything in nature, but we don't talk about those because they're not useful for physics. We only pay attention to the mathematics that works. So from our perspective, it looks like mathematics is unreasonably effective, but maybe we're just ignoring all the mathematics that isn't effective. But even granting that, I still think there's something remarkable going on. Let me try to get at it from yet another direction. When we do physics, we're always looking for simplicity. We don't just want any description of nature, we want the simplest description, the most elegant description, the one with the fewest arbitrary parameters. And remarkably, nature seems to cooperate with this desire. The laws of physics, as far as we can tell, are simple. They're not arbitrary or complicated. They can be written down in a few equations that fit on a t-shirt. Now, mathematics is also about simplicity and elegance. When mathematicians develop a theory, they're looking for the most economical set of axioms, the most general theorems, the deepest connections between different areas. They value beauty and simplicity just like physicists do. So maybe that's the connection. Maybe mathematics is effective at describing the universe because both mathematics and the universe value the same thing, simplicity. But why should the universe value simplicity? That's not obvious. You could imagine a universe with incredibly complicated laws, different rules in different places, arbitrary constants everywhere. But that's not what we see. We see symmetries and conservation laws and simple mathematical relationships. It's like the universe is trying to be mathematically beautiful. Or maybe, and this is closer to what I believe, maybe our brains are wired to find simple patterns beautiful because simple patterns are useful for survival. And maybe the universe isn't really simple, but we focus on the aspects of it that are simple because those are the aspects we can understand and predict. Here's something else to think about. Every mathematical description we have of nature is approximate. Newton's laws work great for everyday objects, but they break down at high speeds where you need relativity, or at small scales where you need quantum mechanics. Even our best current theories, quantum field theory and general relativity, we know they can't be the final story because they don't fit together consistently. So in some sense, mathematics never perfectly describes the universe. It always works within some domain of validity, and outside that domain, you need different mathematics. This suggests to me that mathematics isn't the deep reality of the universe. It's a tool, an incredibly powerful and useful tool, but still just a tool. We keep refining our tools, finding better and better mathematical descriptions, getting closer and closer to nature's behavior, but always within limits. The map is never the territory. But then, I think about something like the Dirac equation. Paul Dirac was trying to find a quantum mechanical equation for the electron that was consistent with special relativity. He was playing around with matrices and spinors, trying to make the mathematics work out. And he found an equation that was mathematically beautiful and predicted the electron's behavior perfectly. But the equation had a funny feature. It seemed to predict negative energy states, which didn't make physical sense. Dirac could have said, well, the mathematics is wrong, I need to find a different equation. But instead, he took the mathematics seriously. He said, if the math says there are negative energy states, maybe they correspond to something real. Maybe there are particles like electrons, but with opposite charge. And a few years later, the positron was discovered, exactly as Dirac's equation predicted. The mathematics led us to a new piece of reality we hadn't known existed. This happens over and over again in physics. The mathematics predicts something weird, something we didn't expect, and then we go look for it, and there it is. Maxwell's equations predicted electromagnetic waves traveling at the speed of light, and that's how we discovered that light is an electromagnetic wave. Einstein's equations predicted that massive objects would bend space-time, and we observed that during solar eclipses. The mathematics seems to know things about the universe that we don't know, and it tells us where to look. So maybe the answer is somewhere in between. Mathematics isn't the universe, but it's not arbitrary either. There's a deep resonance between the patterns our minds can grasp and the patterns that exist in nature. Maybe that's because we're part of nature. Our minds are physical systems obeying the same laws as everything else. So the patterns we naturally think in terms of are the same patterns that nature embodies. Or maybe it's even simpler than that. Maybe the universe doesn't obey mathematics at all. Maybe the universe just does what it does, follows whatever rules it follows. And we describe those rules using mathematics because mathematics is our best language for describing patterns. When we say the universe obeys an equation, we really mean the universe's behavior matches the predictions of that equation within our experimental precision. It's not that the universe is solving equations. It's that our equations are good descriptions of the universe's behavior. But that still leaves the question, why are our descriptions so good? Why can we write down a simple equation and have it predict the outcome of experiments we haven't even done yet? Why does extrapolation work? If I drop a ball 100 times and measure its fall, I can write down an equation and predict what will happen the 101st time. But why should the future resemble the past? Why should the same mathematical pattern continue to hold? That's actually a deep philosophical question that goes back to David Hume. We assume the laws of nature are constant, that they don't change from one moment to the next or from one place to another. And so far, that assumption has worked out. But we can't prove it must be true. It's an article of faith, in a way, that the universe is mathematically describable because it's consistent and regular. Maybe that's the real answer. The universe is mathematically describable to the extent that it's regular and predictable, and we don't know why it's regular and predictable. We just observe that it is, and we're grateful for it, because if it weren't, we couldn't do science at all. If the laws of physics change randomly from day to day, mathematics would be useless. But they don't change, they stay the same. And that constancy is what makes mathematical description possible. So in the end, I don't think I can give you a completely satisfying answer to why the universe obeys invented mathematics. I can tell you it's not as simple as either the universe is mathematics or we invented mathematics and got lucky. It's something subtler. It's about the relationship between minds and nature, between the patterns we can think and the patterns that exist, between the tools we build and the world we use them on. What I can tell you is this: the fact that mathematics works is not something to take for granted. It's a profound clue about the nature of reality. It tells us that the universe is comprehensible, that there are patterns we can find and understand and use to make predictions. That's an amazing fact. It didn't have to be that way. We could have been born into a chaotic universe where nothing made sense, where every event was random and unpredictable, but we weren't. We're in a universe where mathematics works, and that's worth being amazed about, even if we can't fully explain why it's true.